Okay, good afternoon, everyone, and we're starting our Solver colloquium and solar webinar on solar physics. Today we have Qili Zhang. Qili Zhang received his bachelor degree from University of Science and Technology of China in 2012, majoring in plasma physics. He got his PhD from University of Maryland in 2019, advised by Jim Drake and Mark Svidak, with his dissertation on particle heating and magnetic reconnection. He is now a postdoc at Los Alamos National Laboratory. His work focuses on particle heating and acceleration in magnetic reconnection. Today, he will present his recent work published in Physical Review Letter about the efficient particle acceleration in 3D magnetic reconnection. So, Qili, please go ahead, and I will give you a warning 5 minutes before end of your talk.
Right, thank you. So you can see my slides and the cursor clearly, right?
Yeah.
Okay, thanks. Yeah, thanks, Gregory, for the nice introduction. And it's my honor to present today in Solver Colloquium. And thanks for the invitation. So as Gregory said, I'm Qili Zhang from Los Alamos National Laboratory. And I would like to thank my collaborators in Los Alamos and also Xiaosani from Dartmouth College. So magnetic reconnection is a physical process that can efficiently accelerate particles to very high energy. One amazing example is the solar flares, which is the most powerful particle acceleration phenomenon in the solar corona. And that's why we are in the Solver collaboration to studying it. But it is not straightforward to understand how magnetic reconnection can lead to such efficient acceleration. And today, here I will show you some of our recent steps towards this critical problem, and which is also recently published in this VRL paper. And specifically, it is about the efficient particle acceleration in 3D reconnection enabled by the fluxual King instability. Okay, next. Okay, so as I said, the magnetic reconnection is a physical process that converts magnetic energy into plasma kinetic energy, including high-speed flows, hot temperatures, and non-thermal high-energy particles. And as is, this is through the change of magnetic topology. As is illustrated in this picture, when these field-to-field lines pointing to opposite direction from this upstream region come to each other, they can reconnect and turn into these two highly curved field lines. And the magnetic tension will then make these field lines contract and shoot out like a slingshot with the order of Elfman speed. And as these field lines contract at downstream region, the magnetic energy will be released and turning into the other forms of energy, like we mentioned. And so the reconnection should be most impactful when the initial magnetic energy is much larger than the plasma kinetic energy. In other words, when the plasma beta is low. And the reconnection can happen in magnetized plasma, like, as we mentioned, the solar flares in the solar corona, at the Earth's magnetotail, at Earth's night side magnetic fields, and also in laboratory plasma. For example, this is a tokamak, and reconnection can happen on its magnetic fields. And in the case of the solar flare energy release, some large flares can can produce high-speed flows more than 1,000 kilometers per second and heat the plasma to more than tens of millions of degrees Kelvin and accelerate the particles to nearly the speed of light. So it is a pretty explosive and intensive phenomenon. And that's why we study it here. And on the other hand, this simple picture here, only shows the magnetic field in the reconnection plane. In general, there can be also magnetic field components out of this plane, which we call the guide field. Okay, so let's look into the solar flares closely. This is from Bin Chen's Nature Astronomy paper. So this is the sun, and this is the solar magnetic field in the solar corona. And this is a region with microwave emission produced by energetic electrons from the solar flares, these color regions. And we zoom into this region with emissions and rotate 90 degrees, shown on the right. This bottom is the solar surface, and this balloon or this circles is erupting flux rope, or we call this coronal mass ejection, being launching up into space on the top, to the top. And these few lines, you can see they come out of the solar surface and go out and come back in. And this here, there are few lines pointing to opposite direction that come together so that reconnection can occur here to release the magnetic energy, producing these energetic particles radiating in microwave, X-ray, soft X-ray, and even gamma rays. And if we look at these X-ray observations shown on the right, these energy spectra, we will see that the electrons have these hot thermal components, and also these non-thermal power law components extending to, in this case, up to MeV energy. So it's pretty high energy, but there's even higher energy emission in the gamma ray range, which is another power law produced by the protons, energetic protons, extending up to GeV energy. And this energetic ions produced by solar flares can travel, some of them can travel into space and observed by our satellites, which is what we call the solar energetic particles. And our satellite can measure them, not only the proton, but also the other heavy ions from the solar flares. Energy versus the fluence. And we see that they all have this power laws extending to higher energy. And this power law slope is similar between these different ion species. So we have seen that both electrons and ions can be efficiently accelerated into power laws in the solar flares. But in addition, we see that the number of energetic electrons and number of energetic protons indicated by different emission fluences are proportional to each other, more or less, across several decades of different sizes of solar flares, suggesting that the acceleration of protons and electrons are well correlated to each other. On the other hand, we also have observations, in situ observations at the magnetotail, where the plasma beta is as low as that of the solar flares, but with a much smaller system size. At the magnetotail, our in situ measurements have also shown us that both electrons and protons can be accelerated into this power law spectra, extending to, in this case, hundreds of keV. So these observations above tells us that there should be a common particle acceleration process in low beta reconnection, either in solar flare or magnetotail, for both electrons and ions. But the underlying physics, is still not well understood, since the previous studies failed to produce this simultaneous electrons and proton power laws in first principle fully kinetic simulations. And that's the problem we will address in this talk. And we have seen this solar energetic particle spectra from the flares in previous slides. And among these particles, interestingly, people have observed an enhanced ion abundance compared to the corona value for these lower QOVM ions, and also the helium-3, and also helium-3, suggesting a more efficient energization for these ions in the solar flare, so that more of them can travel into space and observed by us. And this is a famous preferential ion enhancement problem in solar flares. And it is a long-lasting open question in the solar community, despite many previous theoretical attempts. So, so today we will focus on the acceleration of protons and electrons, and these special properties of heavier ions acceleration in solar flares is ongoing project currently being under exploration. Okay, so let's review some previous theoretical works. The previous recent studies have demonstrated that a Fermi-type acceleration mechanism is the major acceleration mechanism in reconnection. And as we mentioned, reconnection will result in these highly curved magnetic field lines shooting out like contracting and shooting out like slingshots with the order of Elfvin speed. And as particles go across these contracting field lines, it will get a kick from this outflow and get twice of the outflow speed, and in the same time get some energy. But in order to get to much higher energy, these particles will need to get kicked back and forth by many of these slingshots and get to higher and higher energy. And so this is a Fermi-type acceleration. And this acceleration is associated with the curvature drifts of these particles in these curved field lines along the electric field perpendicular to these field lines. And this perpendicular electric field is associated with the E cross B outflow of the Elfvin speed. And as demonstrated on the right, this Fermi acceleration associated with this curvature drift is the dominating mechanism for these high energy particles, in this case, the electrons, contributing the strongest acceleration rate for these high energy particles compared to other acceleration mechanisms. So this Fermi mechanism, since it's driven by the magnetic field curvature, and the magnetic field curvature is strongest when the guide field, the outer plane field, is low. In other words, in the low guide field regime. So the Fermi mechanism would be most efficient in this low guide field regime, and it can gain the most energy in this regime. But we might ask, how realistic is this low guide field regime in the solar flares? And we can see that there's also observation evidence that suggests the low guide field reconnection is possibly happening in the solar flares during its particle acceleration, and as shown by Bin Chen again. So this famous observation of this famous September 10, 2017 large flares profiles are in good consistency with an MHD simulation in a low guide field regime with a guide field to reconnecting field ratio of only 0.3. So you see that they are in good agreement and lying on each other. At least during this time when the flare produces strong energetic particles radiations. And there's also other works in solar collaboration that suggesting the low guide field connection could be happening during the acceleration. And let's back to the theory side. A byproduct, at the same time, the byproduct of reconnection is these magnetic islands, which forms between every two reconnection sites. And in 2D reconnection, the particle acceleration would be limited by this magnetic islands. The Fermi acceleration would be limited by these magnetic islands, trapping these energetic particles within the islands, these red densities, and stopping them from fully access these contracting field lines at the reconnection exhaust However, in the 3D, things are different. When you have a significant guide field, the reconnection system will generate this kind of oblique tearing flux ropes overlapping with each other to create this field line chaos. And this field line chaos will enable the particles to spread throughout the reconnection layer and fluidly assess this contracting field lines at the reconnection exhaust. As a result, there is more efficient acceleration in 3D versus 2D. And it was further suggested that this efficient acceleration in 3D could help to form the power law spectra for the electrons. And as demonstrated here by Xiaozhan Li, these in the 2D, these high energy electrons don't have further acceleration over time, while the lower end, and while there's more and more lower energy electrons coming in. As a result, this spectrum is steepening over time. So it does not form a sustainable power law spectra. But in 3D, these high energy electrons can be further continuously accelerated while this spectra has a sustainable slope. So it forms a sustainable power law extending to higher energy. However, this mechanism of field line chaos, shown on the left, only applies to the regime with a higher guide field, in the strong guide field regime. But in this regime, the Fermi acceleration is inefficient. So we have this question: can we have this low guide field and field line chaos at the same time, so that the Fermi acceleration could be the most efficient? And that's also a question we will answer in this talk. And just to also point out that there is many studies on 3D reconnection with this reconnection-driven turbulence in the recent years, and both in kinetic and MHD simulations. So the 3D turbulent reconnection is the frontiers of research. Let's look at some highlights of this talk, the results. We will mostly focus on the 3D reconnection in the low guide field and low beta regime. And we'll discover a new mechanism to generate the field line chaos in reconnection, even with a low guide field. And what the low guide field and the field line chaos together drives efficient thermal acceleration for ions and electrons simultaneously into this power law spectra for the first time in fluid kinetic simulations. And we also revealed the physics that controls the low energy bounds and high energy cutoff of the power law spectra. So as we mentioned, we used 3D kinetic simulation to model the reconnection in the low beta and low guide field regime. And here we show a 3D image of the current density. And we zoom into part of the reconnection layer to make it clear. Here, X is the reconnecting field direction, and Y is the guide field direction. And these things are the the magnetic flux ropes generated from reconnection, or we call magnetic islands in 2D. And we see that these flux ropes are subject to this flux rope kink instability, which tears up the otherwise closed flux surfaces and makes the system turbulent. We can show a movie on the right to make this clear. I need to change my cursor first. Okay. So as we see, we zoom into the outflows, one of the outflows that's flowing to the left, and we see these kinking flux ropes flowing with the outflow, moving with the outflow while kinking to make the system turbulent. We can see again. Okay, so we see this fluxural King instability is making this turbulence fluctuations. And it will also show on the bottom the Poincaré type plots of the magnetic field lines, these color dots, in this reconnection plane X and Z. And these different colors of the color dots represent different flux surfaces. The background, this orange color is the energetic electron density. And these blobs are the magnetic islands, or what we call the flux ropes. And we see at this reconnection layer, this fluxural King instability have driven this field line chaos that mix up different colors representing different flux surfaces. So this is a field line chaos from the fluxural King instability. And according to the criteria of this M=1 King instability, namely the safety factor at the edge of the flux rope Q less than 1, we can find that the instability or the chaos can be triggered when the domain size in the y direction, Ly, exceeds a certain threshold scale as pi bgd, where bg is the guide field to reconnecting field ratio, and d is the diameter of the flux rope. And d is typically 1/10 of the domain size in the x direction, Lx. So once Ly exceeds this threshold, field line chaos can be triggered, and as a result, these energetic particles can spread out of the flux ropes throughout the reconnection layer. So particle spreading. We have seen this case above the threshold. On the right, I'll also show you a case below the threshold, where it has this kink stable flux rope. And also from this Poincaré plot, this magnetic field lines is more or less laminar with different colors mostly separated from each other, different flux surfaces mostly separated from each other. And as a result, these energetic electrons are also mostly trapped inside the islands. So the King instability just drives this field line chaos and particle transport. So to further quantify how these particles transport from inside the flux rope, let me use a laser again. To quantify how the particle transport from inside the flux rope to outside throughout the reconnection layer, we we trace the test particles from inside the flux rope and calculate their transports from the center over time, as shown on this panel. We have several simulations with different Ly shown in different colors of solid lines from below to above the Ly threshold over time. And we see that this transport is much stronger in these above threshold cases compared to those below the threshold. And to further understand how they transport, we assume the particles just stream along these field lines. And we've got this dashed lines in the same color. We see that these dashed lines have similar trends as that of the solid lines for the test particles, suggesting that streaming along these chaotic field lines is an important mechanism for particles to transport towards outside the flux rope. And these above threshold cases with much stronger transports, they achieve, they assess the acceleration region more easily and achieve the 10 times stronger, 10 times more energetic electrons at higher energy compared to a 2D case, while these below threshold cases only have a moderate increase compared to a 2D case. So this King instability control the energetic particle acceleration, efficient particle acceleration. So if that is the case, we can take advantage of this King instability threshold on the Ly in our domain size design of the simulations, so that our 3D simulation can extend to an unprecedented domain size in the reconnection plane, up to 300 di in the x direction, so that the reconnection and its acceleration can proceed for much longer time. And we show here the time evolution of the energy spectra for electrons and protons integrated over the whole reconnection simulation domain. So this big blob of Maxwellian is the upstream population. We see that as the time goes on, both species, different colors represents different time. Both species evolve into this clear power law spectra, extending to higher energy over time. And this non-thermal power law components consists of about 20% of the number and 15% of the energy of the particles inside the reconnection layer. So it is consisting of, it is a significant non-thermal fraction. And this power law index or indices for either species are shown in the insets. We can look at these blue lines. Its indices are sustainable over time till the end of the simulation. And both species have index of around 4. Next, we can look at the higher energy cutoff of the power law and plot it as a function of time and different domain sizes. As we mentioned, the largest domain sizes of simulations the reconnections can proceed for a longer time so that we can run the simulation for a longer time. And we can see that the higher energy cutoff of the power law keep increasing with time and also increasing with larger domain sizes, which suggests that this power law could extend to a much higher energy in a macroscopic system like the solar flares. On the other hand, we also demonstrate the evolution of different energy evolution of different generation of particles, both electrons and protons, which flow into the reconnection layer to start energization at different time. So you have many different generations. And in each of this generation of particles, you see a clear injection phase followed by a prolonged Fermi acceleration phase. And this injection energy of electron or protons is controlling this low energy bounds of the power law. And this low energy bound of the power law, on the other hand, in turns controls how much energy is contained in this non-thermal power law components. Because when you calculate the energy contained in the power laws, it will integrate from this low energy bound to pretty much infinity. And on the other hand, this injection energy is the energy particle gain when they first come from upstream into reconnection exhaust. And for the protons, this initial injection and initial injection energization is again related to this slingshot effect when they first come across an exhaust. And the energy gains in our regime is scaled as 0.5 MIVA square.
Could you clarify what is the difference between CA and VA?
Oh, that's the same. Both alpha and speed. Is that clear? Okay.
Yeah, but why is different notation in this case?
Yeah, because this is from Joe Darlin's 2014 paper. I should write here because I cited this picture earlier slides. So it's used different notation, but they are the same. But
the same value, yeah? Okay, good, thank you.
Right, but I want to point out that in the simulation, especially in the lower gap view, so I'm very sorry. Oh, no. Sorry, that's alarm. So in the lower gap view regime, as shown by Kobe Agatis or others' works, this outflows in the reconnection is actually lower than the Alfvén speed. It's about only half of the Alfvén speed. So that's also taken into account in this scaling, just for clarification. Okay, so this is the electron, sorry, the proton injection energy, which is consistent with this picture, 1.5. And for the electrons, it's not that simple. Electron has a much lighter mass, so this initial slingshot energization will be much less efficient. So its injection process would be much less efficient, where the parallel electric field could also play an important role. But I'm not getting into that in this talk. But its injection energy is much less than that of the proton's injection energy. And as a result of this different injection, the protons will eventually gain much more energy than the electrons, controlling this energy partition between these two species. Because in the simulation, proton does gain more energy than the electrons. And it was the injection process, and now the Fermi acceleration process after the injection can be elucidated by a scaling analysis below. Here, we evaluate the Fermi acceleration process at the reconnection exhaust, which is driven by the magnetic field curvature. And also we use the particle acceleration theory, and these two will give this following results, which I omit the process, which is written in the paper. We have a prediction for the scaling for the power law index and the particle acceleration rates. And the acceleration rates is defined as the time derivative of the particle energy divided by the energy. And these are the epictetic scaling. Here, B is the magnetic fields in the exhaust, and BG is the guide field. L is the half length of the reconnection layer, and delta Z is the scale length in the Z direction of the contracting magnetic field lines at the exhaust, which is closely related to the scale length of the magnetic islands or flux ropes in the Z direction. And if we imagine if we have a larger simulation domain, the L will also increase proportionally. But at the same time, the magnetic islands or flux ropes will also, the typical size of them will also grow to a larger size. So as a result, this delta Z and L is roughly proportional to each other. And that's why this scaling would be roughly independent of the domain size. And so from our current simulation, we plug in those numbers, we will get a prediction of the index of around 4, which is consistent with our simulations. And in a larger simulation, we will expect to be the same. On the other hand, these acceleration rates have only one delta Z in the denominator. So as the flux ropes or islands grow over time, these acceleration rates will decrease over time. So as this flux rope will grow about linearly, this acceleration rate will decrease, scaling like the constants divided by the time. And so, yes.
Chile, I have a question about, this is Mark Swisdak. I have a question about your key scaling. So for a given run, L is constant, but delta Z I would expect to increase as the run goes on.
Yes.
Which, according to the scaling, means that P should actually increase as the run goes on. But I thought it was the other way. I thought P tended to decrease, that the spectra got harder as the run went on. Am I missing something here?
It gets harder just at the beginning. Right. So when it starts from Maxwellian, it certainly would get, as solution starts, it will get harder. But
But the scaling with P indicates that it should actually get, I mean, as delta Z grows, as the island grows, P should get larger, which means that's suggesting the spectra gets softer as delta Z grows.
Yeah, so here we only use a typical value to have estimate of the index. And so we do not take into account the time evolution effects on the scale on the power law index at this prediction for on the left.
Okay.
Right. And in fact, in the simulation, it's more or less unchanged. Yeah, so this is just prediction based on the typical value. But on the right, we expect that acceleration rate is actually decreasing over time. And by a closer examination on the delta Z in the simulation, we would estimate that C constant is about 0.8. And from here, we can solve the particle energy evolution to get the E is scaled as the T to the C power, which is T to the 0.8 power. And this rough scaling is roughly consistent with both the growth of the high energy cutoff of the power law and also the time evolution of the particle energy for proton and electron over time. Okay, so our results are roughly consistent with the observations. In the case of solar flares, this power index around 4 in our simulations is roughly consistent with the X-ray and microwave observations for the electrons, and also the gamma ray and solar energetic particles observations for the protons. And also the significant non-thermal fraction in our simulation is also consistent with the observations. In the case of magnetotail, we have the institute observation of the energy spectra for both species. And here is, for example, is events observed by the MMS mission at the magnetotail reported by the Ergun. And this is a spectra. And the power index around 4 in the simulation is roughly consistent with the range of index inferred from this event. And the low energy bound, this kind of shoulder in our simulation here, is also agreeing reasonably with those in the observed spectra. Now, what time is it? Oh, I still have some time, so I'll show you some extra material of giving you the brief idea of our related ongoing works. The previous slides focus on the lower Guy field regime. And here, I will show you that we can also apply the similar strategy to a somewhat higher Guy field regime. For example, Guy field equals 1. And as we mentioned, in the high Guy field regime, the field line chaos is instead controlled by this oblique tearing flux loops, overlapping oblique tearing flux loop, as is shown in this XY cut in the simulation of BZ from our simulations. And this oblique feature is the oblique flux loops. And the oblique angle of these flux loops can be predicted theoretically. And we can use this predict angle to predict a threshold on Ly that can be large enough to capture these oblique flux loops inside these periodic domains. And with this prediction of Ly threshold in the higher Guy field regime, we can again take advantage of that and extend our simulations, 3D simulations, to an unprecedented size, also 300 Di in X. And both species also over time evolve into power law spectra, but with a steeper slope compared to those lower Guy field in the low Guy field regime, which means a weaker acceleration in the higher Guy field compared to a lower Guy field, as expected.
You have 5 more minutes.
Sure, thanks. And this slope in this Guy field equals 1 case is also consistent with the previous predicted scaling for the power law index, taking the guide field equals the Bx. So this means that we can also model and understand the thermal acceleration and power law formation even in the higher guide field regime using fluid kinetic simulations. And so just a few brief takeaways in this talk. 3D reconnection can drive the efficient non-thermal acceleration for both electrons and protons into power law energy spectra extending to higher energy over time. And such efficient acceleration is enabled by this field line chaos driven by this Upshur-King stability in the lower guide field regime. And this low energy bound of the power law is determined by this injection process, and the high energy cutoff is growing together with the system size. And for more information, you can also refer to this PIL paper and feel free to contact me. Okay, thank you.
Okay, good. Thank you. We have a lot of time for questions and comments, so please raise your hand and go ahead with questions and comments. Okay, I do not see anyone yet.
May I may I start with
Just go ahead. Yeah, John Bully, please. Go ahead.
yeah the conclusion is that if guide field line is lower, it is better for acceleration. Does the solar community like this conclusion? Because strong flares occur in strong active region, their fields are strong, just naively speaking. And what is the response from the observers to this conclusion?
You mean the low guide field has strongest acceleration, this conclusion?
Yes.
Oh, thanks for asking that. Yeah, so let me get back to our slides earlier. Okay, I get. Oh, and yes, okay. So this slides, well, you can still see my screen, right? Right. So this slide is this 2017 September 10th flare, and it's actually very consistent with MCT simulation with a low guide field, and it's during this particle acceleration phase here, producing such strong emission. And this is one example. And there's also other ongoing works in sulfur collaboration. For example, Chu Zhong's work using the arcade oblique angle to infer the guide field. And it's actually inferring that the guide field would decrease as a function of time during the flare. And it can decrease to below 0.5. And that's a second. That's another observation work. And also, I prepared another snapshot from Joe Darling's archive paper where he used MCT simulation to self-consistently model a CME launch, which also produced a flare underneath. And this black line is the guide fields in his simulation. And initially, as there's a lot of a strong guide field, but then it will decrease. And at least at this time of the highest reconnection rates, the guide field already decreased to about 0.5, and it still keep decreasing to 0. But anyway, so I would say that at this point there's both observations and simulations that suggest that during the particle acceleration in the flares, the guide field is possibly in the low guide field regime.
Interesting result. Thank you.
So,
Okay, more questions?
May I ask a question?
Yeah, go ahead.
Chile,
Hi.
as I understood, thickness of the current sheet in the y direction is important for developing kink instability in flux rods. Can you say that the longer is the current sheet in the y direction, the more efficient the acceleration process, and higher the high energy cutoff?
Oh, yeah, thanks for asking that. Right, so as it exceeds the threshold, the king would be unstable. So the question is whether if it's more unstable, whether it will create more acceleration. And we have at least we have a study here that after above the threshold, I still keep increasing the Ly, but
I see, but what happens if you increase the size of the current sheet in y direction 3 times or 10 times? Did you have any idea about this? Will this process continue, or it will stop at some at some stage?
I see. So first of all, I do not have those simulations. So, but my current understanding is that after it's unstable and field line chaos occur, those particles could spread through the recognition layer efficiently, so that the acceleration already crossed this gap. And if we further make it more unstable, I'm not sure that will further increase the acceleration. I mean, it's already spread throughout, so it may
I'm
not.
just thinking
I
that
have those estimations. Yes.
maybe it will influence the acceleration in arcades. The longer arcades are, the more efficient acceleration can be. Because a y direction actually shows us how long is arcade, or how long is the current sheet in the y direction. The
Right.
longer the arcade, maybe the more efficient the acceleration is.
Victor, perhaps this is a suggestion for Jill to make a few other runs of simulations and answer your question like once.
Okay.
Yeah.
Okay.
So, yeah. So that's a good
So-
thing to explore, but I don't know yet.
Okay, Dale.
Yeah, I was just trying to understand what we're seeing.
It's a little bit hard to hear you. Could you be a little bit closer?
If you look at slide 13,
13. Okay.
trying to understand what we're seeing here. The color table seems to indicate that the white is high current and the red is low current, the dark red. Is that right?
Let me see. Dark red. So no. Yeah, maybe it's not clear here that I have a threshold. Let me see how to say. I have a threshold of the current density below which there would not be. It's not shown here, and my background is white. So what you see is just vacuum, which because of my low threshold of the current density, which filter out those places.
I sense that the color bar and numbers on it are confusing here.
Yeah. So Y is not extremely high.
I see. Okay. And the other question I had was about the when you say that the high energy cutoff is related to the dimensions of the system. You're still talking about very small dimensions here, right? This is PIC simulations.
You are right.
Yeah.
300 DIs. Yeah. So
is that cutoff an observational thing, do you think, or is it reality? The length scales are so large that the system is always going to be in a long system size.
So not sure I hear the last part. So can you repeat the last part?
I'm saying in normal observing conditions, will we always be in this large system size?
Mhm.
Or will the cutoff be seen in, in observations?
Oh, can the cutoff be seen observation? Yeah, you're right that our simulation is almost 300 Di in X, much smaller than what you can observe in the solar flare. So we are just exploring this fundamental process of acceleration. And we use different sizes and time to suggest that it would keep growing with system sizes. And in the microscopic solar flares case, it will be orders of magnitude larger than this. So its energy will extend to much higher as well. And that high energy is what you can observe in the solar flare.
Gregory, can I make a comment here? This is Jim Drake.
Sure,
Yes.
go ahead. Yeah.
So I think as everybody realizes, we're very limited in terms of PIC simulations as how large the domain can be. But I think what Jim is seeing is consistent with what has come out of the K-Global simulations, in the sense that the system size itself doesn't really power law index that much. What it does change is how high the energy of those particles can get in a given simulation. And the K-Global model produces similar results in that larger systems, the power law index doesn't change very much, but the particles can go to higher energy. So we'll have to see whether that prediction holds out, but I think what that means is that the simulations that are coming out now are probably doing a pretty good job on the power law index, but they're not telling us what the maximum energy of the particles is.
Yeah, related question to Qile. Do you think that besides the gap field, for example, the energy cutoff should also depend on other parameters? For example, the plasma beta, because that's basically tells how large is the Arfman speed relevant to the thermal speed. That if that ratio is different, then the session efficiency will be different, right?
That's possible. But that's still under exploration. And I can for the dependence on beta, I can tell you that if we are still in the low beta regime, which like below 0.1 or so, the protons low energy bounds might not change much because the slingshot process is still giving it 0.5 MIV square. So maybe it's still similar for the high energy cutoff. For the electrons, the low energy bound will change with a higher temperature, for example, more sensitively, and therefore we can also explore whether the high energy cutoff change, because I need to check back the simulation. But I don't remember a large change that can caught my attention. So
yeah, I understand that. So you basically assume that the Arfman speed is fixed. In the solar flare case, for example, during the solar flare, when the current sheet become longer and longer, at the higher corona, I think the field will become weaker. So the Arfman speed will change, right? So in that case, even maybe the slope will be similar, but I guess the maximum energy will mean the increase rate will become slower as.
Oh, I see. You're talking about the Alfvén speed that will change in this process, right? So it could change the growth of the cutoff because of this weaker fields and less weaker Fermi acceleration result from that. Yes. So those effects need to be explored using global simulations.
Okay, other questions?
That's my question.
Qile, can I ask a question? This is Bin.
Happy.
So there have been questions on the high energy cutoff. So I'm curious about this low energy cutoff, which you indicate, for example, for electrons is about 20% of MIVA square. so Jim gave a talk, and I remember his number is like 10 keV for MIVA squared. So 20% of it is a few keV. So this, my question is, in your simulation, you show a shoulder or a hump at the low energy cutoff in the electron distribution. I'm not sure if you know, for hard X-rays we do have the coverage for this energy range. I'm not
Right.
very sure if they you know, routinely see this shoulder, or it's kind of a smooth transition from the thermal core to a parallel tail, as in say the K global simulation. Can you comment on the difference, this interesting shoulder in your energy spectrum?
Right. So at least we see that in the magnetotail observation, and I agree that the X-ray in the solar flares is the low energy part is overwhelmed by another big thermal emission, and so it's not easy to observe exactly where if there's shoulder where it is, and I agree with that. And the 10 so-called 10 keV is just an order of magnitude estimate. It could be higher. And in this case, in this event, actually, the MIVA square is like, I forgot, but it's at least 70 keV. But it could be, and that is order of magnitude, but it could vary too. So, so I don't know in the solar flare how large that shoulder could be, but it could be above, and in this case, it's already above 10 keV.
So Chile, in the spectra you show from your simulation, my
Yes.
recollection is you said that that was over the entire domain. And
That's right.
so one has to be careful because that shoulder may primarily come from the upstream plasma. What does a spectra look like if you just look at the spectra within the current layer?
So I would say that at this energy, it's already away from the initial, upstream Maxwellian. So it's mostly in the plasma, in the irrigation layer components. Of course, one can still look at the local spectra. And I believe Xiaochan Li also take a look at some local spectra in this paper. And I don't remember there's a big change in either the power law index or the shoulders. Xiaochan can comment on that if I remember incorrectly.
Yeah, I think the local spectrum basically mostly are similar, but if you're really close to the X point, then you will see maybe more like a thermal distribution. We away from the X points in the exhaust line, and then the spectrum looks similar to the global power law spectrum.
Right.
Okay, other questions?
Yeah.
Can I also make a comment about the energy cutoff in solar flares? I think recent peak simulation, K global simulations, as Jim suggested, we probably show the acceleration can going on for a while, but for large scale, we haven't really put in the ingredient for the rollover of the power law, which I think is related to, you know, in a broad sense, the trapping and the escape of the particles from the reconnection region. And I think that's indicate we want to include maybe some transport component in the model. For example, Xiaochan Li's paper in 2018, we put in an energy-dependent diffusion coefficient. That actually leads to, as an empirical result, that lead to the rollover of the power law distribution. I think similar effects will be included in the future for the models to tell that physics basically.
Okay. May I ask a quick question? So you mentioned that in some cases, at least, protons gain more or much more energy than electrons. So I wonder what are possible observational tests for that. Will it result in some specific patterns in plasma heating due to losses of these protons, or some prediction about the excitation gamma ray lines or something else? So where to look in observation evidence that such more efficient ion acceleration happens?
Okay, thanks for asking that. So at least I know in the magnetotail is already a result that they see the proton gaining more energy than the electrons. So that's in situ observation. And the solar flares, I'm not certain. I'm not expert on that. I'm not certain there's a way, because my recollection is that the lower energy protons don't even have an observation signature at this point to tell. We only have those gamma rays, and sometimes I have these energetic particles, so energetic particles. So I'm not sure how to tell the collective energy from the protons.
if the dominant container of energy, then this energy must be lost in collisions, and this will show up, for example, as plasma heating, but maybe pattern, temporal pattern or something else will be different compared with heating by non-thermal electrons.
No, I'm not sure.
Okay, good. Any other final questions or comments? We are in the second hour already.
Yeah, I just had a question for Chila.
Yeah, please go ahead.
So this was a guide field of 0.2, of course. So what, if anything, do you think might change significantly if you went all the way down to 0?
For
0.2. Go ahead.
I do not expect a huge change, a significant change from 2.2 to 0, in the sense of the Fermi acceleration power from the magnetic curvature. So I don't expect a big change, but that can be checked when I get a chance.
Okay, good. So likely we have to round up the discussions. Very interesting talk and very interesting discussion. So thank you very much, and let's meet in December at our next meeting. So thanks. Bye.
Thanks, everyone.